Okay, so let's talk about AI perception. Originally, this lecture was actually titled AI sensory systems or sensing or something like that. But the broader term for, sensory input or or receiving stimulus from sensory input is actually perception. Ironically, the name of this microphone is perception. And I was on the Unity perception team, so I know a little bit about perception. But it's quite a broad topic, so let's go into it. And we'll be talking largely about perception in the context of AI in games and how that AI perceives its environment. So how it's sensing things, like how do I know that I'm 10 feet away from the user, or how I know that I'm about to go over a cliff. So quickly, a reminder, production system has a sort of condition action pair, and it defines a single chunk of problem-solving knowledge. And working memory contains a description of the current state of the world and its reasoning process. The actions of production rules are specifically designed to alter the context of working memory. So that's sort of the definition of a production system. You have a set of rules that are designed to change the contents of memory. You recognize, act, and recite and do it over and over again. So this is sort of the definition of a production system. This is, I think, one model, just by the way, but we'll be using this throughout this lecture. So working memory is often the environment and the sensory system for a game NPC, right? You have an NPC in a game, and you have to have that, interact with the environment in such a way. This is based, and a lot of this lecture is based originally on a talk by Tom Leonard that gave at GDC some time ago. I could not find that talk. I did find a more recent GDC talk on AI sensory systems. So I'll be talking to this lecture a little bit more generally than otherwise, because I haven't been able to watch that Tom Leonard talk that was referred to in here. But with that said, a lot of the ideas in this lecture are pretty general, and so regardless, I do recommend you check out this GDC talk on AI sensory systems, which is a little bit more recent. So let me move myself again. Perception is sensing, so from now on I'll be calling it sensing. But what does sensing mean? And in our case, it's actually kind of a metaphor. It's not really the real thing. When we sense the environment, human beings, we're receiving photons from the environment. It's hitting our retina, right? We're not looking at an image. So even computer vision is a far simplification of what's happening in our bodies, because photons are stochastic in nature. They're random in much more ways than just where they hit on our retina. Further, right, when I sense the table, what is that? It's like the electromagnetic interaction between the atoms in my finger and the table pushing and generating these signals in my neurons that are being It's a very fucking complicated thing. The way that even the simplest organism can sense its environment is essentially we barely understand it. We understand it at a very high level, but we barely can kind of go deeper than that level, and definitely beyond an organism of a few hundred cells. Can't really tell you exactly what's going on and have to treat it like a statistical system. So, with that said, when we talk about sensing in games, we're very much simplifying it down to almost like how we perceive the world from our consciousness, from our conscious bias of ball go this way, or he went to the store, and things like that. So we're very much at a high level here. So sensing is much in a game, much like a other game system. It's an emulation. It's not a simulation. We're very much not doing. I mean, this slide mentions computer vision, but I even just told you computer vision is a gross, emulation of what actually is happening. So we're trying to do a little bit more than just simple decision machines. We're trying to magnify its value, trying to represent knowledge in some way that is useful and interpretable. Interpretability in knowledge representation is very important for game AI, because in a general machine learning problem, I don't need to interpret the knowledge representation as long as the model outputs accurate results. But in a game, I'm not looking at the accuracy of the results the AI is my results. I need the AI to always behave the way I want it to behave. And so interpretable knowledge representation is everything, right? In other words, like the agent went to the tree because it was hungry needs to be a logical statement I can make about the agent in an AI for games, because otherwise, like, why did the AI go to the tree? We don't want it to go to the tree, but it keeps going to the tree because the knowledge representation is not interpretable. Like, we don't know why it's going to the tree. Let's throw it all away and not do AI anymore. So further, it has to be relevant to the game design, and it may even involve game logic. So there's a lot to kind of that goes into sensing. The sensing is really kind of secondary to the game design, right? So it's a product of game design, not the other way around. You sense the design of the game. So you're making a game of tic-tac-toe, there's not much sensing going on, right? Sensing is literally looking at the data in memory. Sensing has to be efficient because it can't take up too much processing power, because you want to maintain that for the actual game. It needs to be only as complex as it needs to be to result in the results that we need. And it needs to be perceivable and understandable by the player, but also by the designers. And it does not include senses impossible to provide player feedback for. Like, why are you sensing something that doesn't ever get used? So this lecture is going to go a little bit into Half-Life, the original Half-Life. So some other Half-Lives have come out since then, but let's talk about it. So Half-Life sensory systems require sort of strong tactical and presentation elements. Like, we need to know where things are and people are. There's sight and hearing, right? If a player is around the corner and does something loud, we want the AI to know about it. So in a way, hearing is a proxy for that. Some kind of information management, right? Like, I may be reloading and then shooting and reloading and shooting, and those are two different states, and I may be doing two different things in those two different states. And I'm talking about from the perspective of an AI, not from the user's perspective. And we may need to sort of leverage basic senses into our behavior. So for example, I'm an agent and I'm shooting at you, and then I'm hiding behind a box or something. So there's the sort of basics. I'm looking at the world, I'm listening to the world. This is sort of an active behavior. It's not passive. I need to be sampling the world in these look and listen modes. And I use quotes because look and listen in this context may be nothing like your version or human version of looking. I'm not looking at an image of the world even. I'm likely like just figuring out how far I am from certain key points in the world or from the user. Even listening is largely just drawing lines from audio sources as reported to me by the game engine. And again, the simpler the better in the context of performance, because if I can leverage the abstractions of my game engine and make it less realistic but same effect, I'm just saving compute cycles I can be using for other things. So this kind of digs into this of like limiting the work we have to do by leveraging the design of the game, right? And it can even be event-driven, and that's okay, right? In a way, event-driven sensing systems are very, very ideal and efficient, because if your game is event-driven, meaning I'm only going to respond to events, it means that you can't sense anything between those event intervals because nothing has changed about your world, right? So that's one thing to kind of think about. You can only sense change because if you sense what you've already sensed, you've sensed nothing new, and that's not sensing anymore. Sensing by definition is almost a differential kind of process. It's sort of like the object was here and now it's here. You gain no information by saying the object is here and it's still here. The only way that has information is if the object is here and it's still here, but you thought it was going this way. Like it's moving and then it's... So the differential information is really the only information that matters. Like static information is no longer is not relevant. So here's a kind of example of a maybe a sort of like pseudocode for behavior for AI, right? If I'm close to the player, then begin looking around, gather a list of entities within that distance. For each entity, I want to look for them, and if they're in my view cone, and I can raycast my eyes to their eyes, then if they are the player, and blah, 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 blah. And then you can kind of see what this sort of behavior tree, this is almost like a tree of behavior, like you could take this and turn it into a tree, looks like. right? And this is a very high level, right? Like, if I am close to the player, then what does close mean? What does a player mean, right? Gather a list of entities within a specified distance, like everything, like the trees, like the meshes, like these objects. What's an entity? So once you start to build out these systems, you start to realize, wait, like this goes quite deep, and you have to create a language around this. And so, for example, BTNs or behavior tree networks are that kind of thing. It's just a bunch of nodes with if, else, or other and like flow of behavior that results in some kind of action. And sometimes multiple, right, actions. So here's another example for listening. Begin listening, right? This is going to happen in some kind of time step. And for each sound being played. So I'm not even dealing with the audio, right? I'm dealing with a sound as an entity, right, that's being reported to me by the way of the engine. And if the sound is carrying to my ears, meaning if there's a line of sight or a line of audio, right? Maybe you're taking into consideration diffraction. It is diffraction, but sound goes around corners because the wavelength is proportional to that size of diffraction, like you wouldn't see in light. But it's big enough. Sound is a very long wavelength, and so you have maybe you're hearing something around a corner, or it's bouncing off of something, right? And then you can add the sound to the list of sounds, and if it's a real sound, then signal that you heard something. If it's a small, it's a smell or a pseudo sound, then signal that you smelled something. So you can actually leverage listening into smelling as well. You can kind of see how you could build this. So it's essentially like collecting a bunch of observations and collating them in some interesting way. So the type of observations have to be some kind of relation and have some kind of purpose in your game, right? It's related to some property of the AI. It's a relation to a sensed object to the object of the AI, or it's relevant to the player experience, such as, the player is bored. So when the player is bored, maybe inject a line of dialogue if you're a sort of co-op, like a co-op type AI that's there to work with them. Or if the player is doing something stupid, you can kind of tell them, hey, don't do that anymore. You should go over here. Or if they're lost, or if they're stuck in a loop, you sort of try to sense that no progress is being made in the game, and you sort of add hints progressively. So optimization is generally derived from the game mechanics of these AI systems, right? So these systems can be very specific to a game, to the kind of game you're building, to the engine. Sometimes they're very not portable. And also, they're going to be only limited to the things that actually affect the player experience. So, for example, you're not going to sense a bird flying above unless that bird is tantamount to the experience of the user, or there's some kind of real reason that you need to pay attention to birds. Vision. We'll talk a little about vision in the context of games. This is, I think, a little bit old now. But when I say old, what I'm really saying is that, like, AAA games don't use this technique as much as they do now, like they used to, and a lot of indie games still do. Smaller games, smaller studios, like this is still, a lot of things are becoming more sophisticated as budget goes up. But vision, in the context of an AI in a game, just is dependent on the view distance within a cone and line of sight. So you have to take into consideration things like your eye position. So you're not just like an infinitesimal point in space. You might actually have two eyes, right? And you can get quite deep here. And if your ray is not being obstructed, meaning it's not intersecting anything, and you can ray cast and hit the object, then you can see it within a view cone, right? If you can ray cast outside of the view cone, so actually frustum culling can be a first stage for AI, much like you do for graphics, because you can say, well, I don't even care about objects outside of my view cone. And so now you can raycast to a significantly smaller number of objects. The operations tend to be ordered from least to most expensive. This is very similar to collision detection, if you are familiar with that. Vision is essentially collision detection, except you're raycasting. It's almost like ray tracing, but you're only tracing one array. And you're not doing the lighting calculation, and so you can raycast from eye to eye or eye to box or whatever it might be. You can do the frustum culling, as I mentioned, and it can sort of get around. It's not as complicated as cameras, but it's sort of similar. Controlling senses for enjoyment, I kind of mentioned this already. It kind of, you can use AI for sensing that the player is doing dumb stuff, or if you're not visible. Say you're an AI trying to lead them through a complicated maze. Maybe you don't want to keep going if they're not looking at you while you're going. Sound is simpler than vision because sound does not always require a raycast. It can often require like just a range, a region, and then you can sort of go from there and say, oh well, if it's bouncing, what's the distance, what's the fall off, things like that. AI for sound, it's more about determining, is that something I should pay attention to? Okay, a sound got played in my vicinity, I'm within range of it. Is it important? So yeah, like I said, this game, Thief: The Dark Project, slightly older game. I haven't played it, but you can see one of its kind of notable features was that it involved a lot of stealth, and while you're stealthy, you're producing less sound, but sound was the mechanism for triggering enemies, and it was really all about being quiet so you didn't have to fight, because if you did, you were just sort of outnumbered or whatever it might be, and so you got this penalty by way of sound for disturbing the environment. And so the cost of discovery and combat was really, really high. So you really were incentivized to be quiet and sneak around and not make noise. In that sense, the senses of the game were kind of the focus, right? And that was sort of what really made the game. I remember another game a long time ago, I think it was like Splinter Cell or something, similar idea, where it was all about staying in the dark, right, not making noise. More recently, Valheim does the same thing with sneaking, and then as soon as they see you, they'll respond. So this mechanic, I'm sure a lot of us are very familiar with. There's a large spectrum of tunable states in AI, right? Like you shouldn't necessarily always be on alert, and you also and sometimes when there's like a big battle zone, like maybe you're not paying attention to every little sound either, right? So it's sort of maybe there's a quiet moment and everything's very heightened, and when there's a loud moment, everything's kind of subdued, and you maybe want to have this like a control. Or in more traditional ML context, this is often called a temperature. And if you're using some kind of distribution with a threshold, right, what you do is you multiply the distribution, you take it to the power of this temperature factor. So above 1, you're sort of making it more spiky and so more sensitive. And when it's below 1, you're making it flatter and less sensitive. Yeah. Sorry. Let me kind of talk through this a little bit. Let me just take a moment and get some water. Okay, so some requirements, like as we mentioned, we may have some spectrum we want to deal with. We also may want to operate on a variety of different objects, and more often we'll notice some player activity even when the player's not present. We want to kind of notice maybe things like blood on the ground. More notably, I think, is shadows, right? Like when we see shadows, like an AI can sense that a shadow means that there's somebody there without being able to, directly see them, or a big performance challenge, right? Like some kind of issue that is high performance, that requires a lot of, performance from the user, and detecting that is the case, that it's a difficult portion of the game. We also want it to be stable and intelligent. We want it to have a kind of an analog feel, right? We don't want it to be bad feedback, right? Players and designers understand inputs and outputs, and so we want to kind of build on that in the sense that we want to make it kind of predictable. We don't want the AI to sort of just like blow up and do random things. And in that sense, we want the outputs of the game, of the AI, to match with the expectations, the learned expectations. So if you have, for example, an AI throughout the game that is doing one thing, you don't want it to all of a sudden be doing a different thing unless there's a context that's changed. You want to make sure that those cues are learnable by the user. And also, you kind of want to have a limited number of things. If the user has to constantly be aware of too many things that affect the AI's behavior, eventually they'll just get overwhelmed and walk away. So in a way, you kind of want to limit the amount of stimulus that your AI can perceive, because if not, then the user gets overwhelmed, right? Of like, oh, I have to pay attention to everything, and that's annoying, right? So there's one hack around this, which is make the AI human-like in its perception, and that tends to be a one, like that only counts as one, right? If the AI senses you via vision or smell or sound or thing, all those things are like valid expectations. The user doesn't have to kind of behave a different way than usual. But if the AI is paying attention to like what's in your inventory, slot number 3 and 5, but not 4, but except on Tuesdays, it's sort of like, okay, I don't really care anymore. I think it sounds really artificial, but one of the notable places you find this is in like a game like Hearthstone or like gathering games or RPG kind of Dungeons and Dragons type of games where, you know, it's just a combinatoric mess of all the different things, and many times players will sort of get to a certain breaking point where they care about things, and once you get past that, it's hard to keep them on the line. So similar to Half-Life, right, what we need is we're going to be doing view cone based raycast vision for this is for Half-Life. We have a simple hearing system, and we have these hooks in the games around optimization mechanics and the pseudo-sensory data, and we can sense gathering decoupled from this decision process, meaning we're sensing, but that's unrelated to the way we're making decisions, and decisions are unrelated to the way that we're sensing the world. So they're two separate systems, but obviously interplay very closely. It's different than Half-Life because we're, you know, object-oriented with independently scaled components. So, you know, we're, I'm not really necessarily sure what this is about and what we're comparing this to, because I think we are talking about Half-Life, but okay. I guess maybe this is a system that we want to build. I'm not really sure, but either way, you know, one of the things that Half-Life doesn't do is generally all the systems kind of work together. This was like the original Half-Life, and you know, it wasn't so. I mean, it was object-oriented, I thought. I mean, it was based on the original Quake engine, but perhaps the AI actually had a lot of issues in the original Half-Life, if I recall. There were a lot of ways to trick it. Like, for example, when it was reloading, it wouldn't acknowledge other AI behaviors, and so sometimes you'd be fighting an AI and would have to reload in the middle of the game, but all the AIs would no longer respond to stimulus, and you could just kind of like wait until one of them reloaded and take a shot at them or something. I forget. It was just a, you know, early performance limited computer program at the time. So yeah, the Half-Life didn't have states per AI, and yeah, so on and so forth. So going through the kind of components, this is again based on Tom Leonard's talk, which I'm not aware of, but this is a pretty valid type of, like, so call it a system topology, right? Where you have a game object, you have a player or an AI. We're mostly interested in the AI of it, right? We see the visibility, the game objects are visible or not. So this is almost like an entity component system. The visibility determines whether or not it's there or not. And the AI has some kind of alertness that controls view cones that then the AI senses own. There are configurations that determine what the view cones are. The AI senses interplay with an awareness system and a sense link, that these link to other game objects. So you can kind of see there's a loop between the AI and all of the other possible objects in the world. And if you're not familiar with this type of diagram, it's what's called UML, or Universal Markup Language. Doesn't look like markup language, but it is described as such by a markup language. And it's pretty useful to know about. This triangle means type of, right? This means owns or depends on. The star means, you know, one to many or one. So that's there's a way to kind of read this deeper if you'd like to spend some time on it. So awareness, the awareness system has a range of discrete states. It's certainty of presence, location, or identity, and it's only qualitative value exposed to other systems or designers. So it's basically only intended for internal systems. And the alertness is basically an agitation state directly. It's related to awareness, and it feeds back into the sensing system. So, if you look back at this system, right, the AI senses basically triggers is by the awareness and so on. And the alertness is then triggered by the AI senses. The sense links, they relate the object to others. So as you can see here, the sense link, there may be many sense links to the game object, right? And this sort of tells you what other objects are sensed by this object. And what's interesting here, right, is this game object may be a player or an AI, and the player needs to sense other objects too. But you can see for every object, there may be many, many, many other objects. But for you're only dealing with one AI per many objects, so it's like one to many. It stores all the relevant information of the other systems, so you might not need to have access to the entire object. You just need to know like where it is and what it's doing. And so it's almost like a I forget the name of the design pattern here, but it's not an adapter. It's like almost like a decorator of some kind. And it also stores hidden data that's cached for optimization continuity. So say I'm in every object is one to many to every other object, right? So you have many to many in effect. And so if you have one object that's looking for others, it may be querying things and things like that. And the sense link object system here may be saving that information. So the next time it gets hit by another object, you don't have to redo the calculation or redo the memory access or something like that. So that's, I think, something to pay attention to. The sense link is a sort of intermediary. Like in theory, you can kind of imagine instead of this line going to the sense link, it could just go to the game object, right? Like, and the AI has access to every game object, and that's cool, but that's pretty heavy, right? The game object it may have lots of other systems that you don't care about. You just care about its location. And so the sense link may just be an interface or a decorator to the game object that gives you access to that in a cached way. So it's creating more memory of this particular thing, but it's like sense link could be, for example, it doesn't have to be object oriented. It could be a data oriented design type of system, which is basically just a database, right? It could be just a static array, right? So sense links are kind of similar to memory or knowledge, and they're transmittable through verbalization observation. They can also be manipulated by the logic and scripts of the game. And so this is sort of some examples of this, right? You have an AI, it senses a dead AI. This is low awareness, first-hand sight. Here you have a sound, it's medium awareness, it's first-hand sound, and so on. And you can kind of see how these things interact and interplace through the sense links. Visibility, we talked already about this in the context of vision, but it's a property independent of any viewer to any other object. There's lighting, there's movement, there's exposure. You can kind of start to apply. It's not like you have to render it from scratch, or maybe you do, right? I had a friend of mine who took a game engine like Unity, and in it actually built a fully computer vision based driving AI. So it was using computer vision to determine where the road was and how to stay on it. And it was like kind of like an old school line following robot, except in this case, it's actually taking the image, it's rendering an image from the perspective of the car, running that through a machine learning network, and then from that determining whether to turn the wheel left or right. So you could go freaking bananas here, but for our case, maybe we just want to say, oh, this object is in our view cone, but it's moving really fast, so we just saw a blur, we don't know what it is. Or, oh, it's in a shadow and it's not actually visible. Like, we can see it from a projection standpoint, but we can't actually physically see it because it's not reflecting any light. And so you can kind of, again, you're inside the engine at this point, so you can kind of do whatever you want. So this means that it's very much closely tied to in-game requirements, and it depends on what you're trying to do. So one example here, right, it's a shadow, the dead AI is in the shadow, but I can't see it really because even though it's first-hand sight, I can't actually see anything, right? Whereas there's a sound that I heard, but I can hear it directly because even though it's around the corner, it's sound, and so it doesn't really care about corners. View cones, I think we've talked a fair bit about this. They're 3-dimensional or 2-dimensional depending on the game. They're ordered, right? So it matters kind of what the ordering is, like your depth. Things that are closer versus farther do matter. They have angles that describe them, and they're configurable, meaning they're your field of view, your near, your far plane, right? How far do I really want to look? And they may be enabled or disabled based on the alertness. So am I actually paying attention, right? Maybe I'm not paying attention, I'm looking straight at you, but I'm just like asleep. So I might turn off my view cone or narrow it or change it based on certain things. The view cone in this context is actually not the same as a camera, right? Because in a camera, your field of view really affects your image, but here your field of view affects your ability to perceive something changing in your environment. And as you know, if you're not looking at, like, I could be facing you but looking at something else. And so there's a little bit more nuance that goes into the view cone for an AI perspective, for an AI use case, right? You may want to narrow the field of view based on how attentive I am. If I'm really tired, it gets narrower and narrower. Eventually it goes away. Perhaps I'm like, I just drank a Red Bull, and so I'm like paying attention really aggressively, and my view cone's going to be really wide, or something like that. So I would, you first qualify the view cone in this ordered set, right? And then you presume that it's going to put out a constant output regardless of the position. So it's almost like what you're doing is you order your objects in front of you, you flatten them down, and if it's in your view cone at all, then you pay attention to it. Otherwise, it goes away. So here's an example. You determine the view cone. You feed the visibility information into the cone, into the look. So are the objects even available? Like, is the visibility enabled? And then you generate a discrete awareness. Is the object in this view cone or not? Or what? Give me a set of the objects I'm going to now iterate through, pay attention to. So there's a few more things that matter, right? You're going to be affected by the owner's state. So how wide is the cone, as we talked about? What about peripheral vision? Maybe outside of this cone, I have a secondary cone that there I'm only sensitive to motion, right? Like imagine doing an AI for like a T-Rex, right? If you stand still, it doesn't pay attention to you, but if you move, it does. And then a few other things. So the pipeline is set up of these series of components, and each one of them sort of take in this well-defined data set and output a more limited value. And it's almost like these, like almost these little funnels that go into other funnels and go into other funnels, and each funnel gets smaller, and eventually you get a go left, right? or shoot, or whatever it might be. And each layer is sort of scalable depending on the amount of performance you have available to allocate to it. The end output is essentially just a discrete awareness value for the object of interest. Below that, obviously, is the decision stuff. And the heuristics to you are a black box. Like, you don't know why anything happened. You just know that I should be aware of this thing. So the programmer does the most of the fine-tuning, right? The understanding of the black boxes, the ability to alter the black boxes. That's not available to us as an AI. It's not available to us as a player. And so making this work really well requires a lot of playing and experimenting, and possibly retuning it if the systems change. This is a system that's constantly being addressed, because as you play the game, all of a sudden the AI is too attentive or not attentive enough, and you might have to add more and more layers to kind of compensate that, right? Like I'm playing a game and I have a level that requires like weather, and I need to reduce the attentiveness of the AI to compensate for the weather, because I'm going to have way more enemies in that or whatever. And so this is at the programming level, something that you do, and you create these systems, but then the controls need to be provided to designers at a higher level, right? Again, so take that example of the weather system that affects the alertness, right? What you can do is you can kind of turn this into an alertness dial, and so for a rainy type of scene, the alertness of the AI is like 0.3, whereas in a sunny day with no clouds, it's 0.7. And say your AI's just drank, a bunch of Red Bulls, then it's 0.9, right? So you can give the designers the ability to tweak things without having to go into the code. So here's kind of the pipeline overall. I'm not going to go too deep into this. I encourage you all to kind of take a look, because we can go through it. You know, it's quite detailed, but you can kind of see this top down to the sense link, which is the information that the AI makes decisions upon. And this is more explicitly the vision component. The sound is a little bit simpler because you don't necessarily need to worry about occlusion as much or propagation as much, but you can simulate this as deeply as you'd like, or you can just treat sound as a kind of like point source with a distance. So you just sort of calculate the fall off. You know, it's like usually an inverse square fall off, like light or anything else, with a magnitude. Right, so sounds are really cool because they generate awareness at a point in space, and there can be very effective ways to communicate things across AI that don't require an explicit way. Like, for example, in one of the previous slides, right, an AI yelling grenade, and then all the other AIs hearing that grenade sound and running for cover. Because the one AI that doesn't hear it because they're out of range won't hear it and won't behave, and here you go, you have some dynamic emergent behavior because they throw a grenade, and the one schlub that didn't hear it is now in trouble. So we've seen this already. This is the awareness component, so the sense link kind of system for sound, and you can kind of hear how look and listen kind of go both into this thing and go into the sense link, which is used to communicate between. So again, this is more of a object-oriented sort of architecture versus a system diagram of what happens. It's more like these systems interplay, and you can kind of hear all the different things. You can see all the different things that have to happen. Cooldown capacitor. The fuck does that mean? Let me just make a really quick comment here because I think that's weird, but like there's no capacitors in code, right? I actually went to school for electrical engineering. So the idea here is that there's some kind of delay that goes into play, right? Like this is, I think, a thing that really matters in AI because human beings respond, and there's the world happens. There's a fundamental, there's a discrete, a continuous nature to the world where things don't happen immediately. Events kind of in this magic abstract world happen instantaneously, but in the real world, like you can measure things, right? Like when a light turns on, it doesn't all turn on at once. Like there's an amount of time that it takes. There's an amount of time that it takes that light to hit my eye. Sound goes at a particular speed. Cars don't just crash into each other instantaneously. They take time. Those times may be very non-intuitive to us as human beings because they're at a very, very small, number. But if you look at the kind of physical world, those numbers are massive, right? The amount of time it takes a car to crash into another car on the order of, the Planck scale is an infinite amount of time. So this is what these things are doing. If you don't simulate some kind of delay in your AI systems, your AI will be like impossible to beat or too reactive, even with all these systems. And one way to do that is you have a ramp up delay. So you essentially go from 0 to 1 with some kind of delta, and that's what the system is doing. Or you have a cooldown, so you have kind of a refractory period during which you just, for example, like you shot the gun, right? Like your AI shot the gun. You don't want to shoot again immediately. You need some refractory period to shoot the gun. Right, because you're not physically simulating the trigger of the gun and the cavity and the barrel and the bullet moving. The enemy is choosing to select that action of shoot the gun, and at that very moment, the gun gets shot. Right, so if your AI was going to choose shoot the gun again the next frame, you've basically in 60 frames have given your AI the ability to shoot the gun 60 times. Maybe you didn't mean to do that, right? So you need to kind of add in some physicality both to the AI and the logic, because human beings, we don't make decisions immediately, instantaneously. Decisions don't happen immediately. Response to stimulus doesn't happen immediately. One of the best examples of this is, right, when you're walking around and you stub your toe accidentally, and in that moment, you stubbed your toe, and you're like, fuck. And then about 100 to 150 milliseconds later, you feel the pain. Because that's how long it takes that sensory input from your toe to travel all the way up to your brain and for you to perceive that feeling. So it can even be as long as half a second. And we've all had this experience. If you next time you do, pay attention to it. It's very interesting because you can actually almost sense the delay. You are aware of the pain before the pain. It's very weird, but it's true. So that's something to kind of pay attention to. And so the highest of either vision or sound is taken as awareness, and data from vision and sound distilled is turned into a single awareness pulse. So this is more talking about the engineering of how to communicate on these sense links, the awareness value, and how to then use that from the context of the AI. Like, how aware am I of this object, right? Like a pan fell to the ground and made a sound. I'm very aware. It's a very loud sound. Versus like a little bug sneaking along. I can see it, but it takes up like 0.1% of my field of view, so I'm not very aware of that, right? So if the awareness is increasing, the filter controls rise up, the time delays, reaction time maybe goes down, and these are all these formulas that we kind of create. We're not talking about them much here about them. If the awareness is decreasing, the capacitor controls awareness descent, so it's sort of this like let go, this refractory period, and it kind of, again, falls into these formulas. I know we're not talking about the formulas. Again, I can't access this talk originally, but these are all very much relevant ideas, and they've always been true, or are very true today. So like you don't have to design your AI system this way, by the way. Like, you don't have to do this pulse thing. This pulse thing is more of a like idea that it's similar to like how your physics engine hits every 10 milliseconds or whatever, or your main game loop may be on a thread that updates every so often to get you to 60 frames per second. And the pulse, the frequency of pulse here, when you're saying pulse, you're really saying how often do we update the awareness of a particular AI respective to all the other AI objects to then allow the AI to change its behavior. That's also, again, could be just your AI engine that runs every 10, 20, 50, 100 milliseconds. And so that's something to kind of think about. Cool. There's some problems that, I mean, everything has limitations, right? This system, as I just mentioned, could be very CPU intensive. It can place demands on systems. It also goes up n squared, right, in complexity, right? For every AI that needs to be aware of every other thing, you just add another n things to pay attention to. So it can be very expensive, and you might want to even layer awk trees and all the stuff that you do to optimize collision detection and rendering on top of this. What about client server? Like, this works really well for single player, but what happens when you have other people playing with you, and how do those systems cohere, right? Let's say I'm playing a game with you and you have an AI agent in there that has to make decisions, but we both have to see it make the same decision. So who wins, right? Like, what if my computer does something different than your computer? Do we communicate? Does it run on your computer and report to me, or vice versa? Or like, how does that work? So as soon as you throw multiplayer into it, it becomes much more complicated. The common solution to this, of course, is to make one player the server player, and then the other player, it's just a puppet, right? One player's server determines all of this, and then the other player's server just gets information about updating this object, and no AI is running on that other one. But then you have latency, right? Now the other user only sees the updates after it's been reported, and one player has more computational load than the other. So here's another kind of set of trade-offs you have to kind of consider. And a lot of things have to be taken into consideration, like the tuning, and this may be a big commitment for the game that you're making. So one final slide. Benefits here, right? You get a simplified, higher level decision, set of decisions that you can make. There's some clean location for expressing, this pre-conscious behavior, and on top of that, you can make conscious behavior in the form of a state machine or whatever. As we'll talk about in the next lecture, this can fall into the behaviors that you want your agents to make, right? Like, hey, apple fell from tree, won't go there, that kind of thing. And then you can also add a lot of really subtle and varied behavior without adding much complexity, because by having this sort of sense of awareness of other objects, you can sort of say, well, I'm aware of 10 objects, but this one 10%, this one like very much, and you can sort of then mix behaviors in kind of a linear, but a very, very interesting way. So that's it for this lecture, and next one we'll be talking about behaviors and how to actually make your stuff do stuff, which will be very interesting.